All right. So we're now in the last chapter, chapter 11. We'll talk about, we're only going to get to 11.3 though, dissolution, electrolytes, and solubility. So we'll just begin with the dissolution process. So dissolution process, we'll talk about some basic properties, maybe some predicting, and explain why some solutions produce or absorb heat when they form. Okay? So solutions are made up of homogeneous mixtures, right? Two or more substances. We put them together and they become some uniform solution. So let's think of maybe uniformity for homogeneous. So the solute and solvent, right? What is it that we're dissolving? Right? If I put some salt into water, the salt is the solute, the solvent is what's doing the dissolving. I'm sorry, the water is what's doing the dissolving, so the water would be the solvent. I put sugar into water, right? Sugar is the solute, the water is the solvent. I put coffee into water. The coffee is the solute, the water again is the solvent. So solutions can exist in three physical states, right? So even solids can be a solution. Right? This is where we get our metal alloys, right? Sterling silver. 18 karat gold, brass, bronze, right? Sterling silver isn't 100% silver. Sterling silver is about 7% copper, 93% silver. Right? 18 karat gold is mostly gold, but it does contain some copper and nickel. But it looks very uniform, right? The gold looks very uniform. The silver looks very uniform. So these alloys can be solid. Then we have gas solutions. Right now we're sitting in a gas solution, right? We're sitting in a mixture of oxygen, nitrogen, argon, right? We can see, right? We're not looking at little specks here. It's very uniform, this solution. And then we have liquid solutions, right? I can put methanol, or I can put isopropyl alcohol into some water and they make a very uniform solution. So with solutions existing in three physical states, right? Air, we'll skip soft drinks here, right? This is going to be in a solid, so palladium can absorb hydrogen gas, right? We have rubbing alcohol, which is a mixture of two propanol, some water. Salt water is just some sodium chloride and water, brass, zinc, and copper. And soft drinks. So soft drinks can look uniform, homogeneous, until we do one thing. Right. If I have a 2-liter bottle or a Coke can or something, I can't see through the Coke can, but the 2-liter bottle, the plastic bottles of soda, we can see through those. So it looks very uniform until we pop the top and we release that pressure. So it is under some pressure, and as we release the pressure, pressure decreases. When pressure decreases, is that the CO2, right? The CO2 gas that's in there becomes less soluble with decreased pressure. And this is why we get that fizzing there, because the CO2 is becoming less soluble in that syrup of water and whatever drink mix that we're looking at. So when we're looking at considering dissolving solutes, let's take a look at these. So we have sucrose, and we have some aluminum sulfate. Is when these are placed in water. Okay. This is solid, this is also solid. Is that here the sucrose then becomes aqueous, but there's a difference that we're going to see here. Put sugar into water and then we get this aqueous sugar molecule. But here, this is what we consider an ionic compound, right? No metal, this has metal, ionic compound. Is that we're going to get 2 aluminum ions, plus we're going to get 3 sulfate ions. Right? So here, these become aqueous. This is also aqueous, right? But we're producing ions here when we just, so covalently bonded molecules dissolve differently. There are exceptions to this, which we'll go over later. But here, ionic substance versus covalent substance, and we can see that ionic substances separate, right? And we create these ions. So one of the things that makes this spontaneous, right, because this will happen spontaneously, is what we consider entropy. So we talked about thermochemistry, but not thermodynamics. Thermodynamics is covered in a 202 lecture. But one of the ideas behind thermodynamics is increased entropy, right? So I want you to think of entropy as disorder, right? Is that this is very ordered, it's very structured, it's a solid, and then when we put in the solution, we got these ions just floating around, it becomes more disordered. We increase the entropy, right? So spontaneous reactions happen with an increase in entropy, right? Here we have this solid, put in some water, and then we get this mixture of ions here, but it's very uniform. This is homogeneous, right? A homogeneous mixture here. But we have split up that potassium dichromate into some homogeneous solution, but it was a spontaneous reaction. So without getting into thermodynamics, what we are going to consider is we're going to consider these two criteria here that favor, they don't guarantee spontaneous reactions, right? But they will favor spontaneous reaction. But again, there's no guarantee. And one of them is a decrease in internal energy, right? Exothermic reactions, right? We light up a piece of wood and it will burn spontaneously, right? Is that we octane gas, right? We can burn octane gas, combustion, right? So exothermic reactions can be exothermic, but so can endothermic, and we'll give you a case or two on that. But here we have an increase in entropy, right? An increase in entropy. So let me pose this other image for you, right? So I'll draw a model up here of some container, and then we'll look at entropy and spontaneous reactions here. Right, it's recording. See it? All right. Again, the third time. Here we go. All right, so these two containers here, when I open this valve here, what's going to happen with these gas molecules? They move. Without any external force, right? Without having to add any additional work, these will spontaneously spread out like this. Part of the reason this happens is because this is spontaneous, is that we get an increase in what we call entropy. And let's think of entropy as chaos. Let's think of it as disorder, right? So things naturally become more disordered, right? Would we expect this to spontaneously, all the molecules move to this side of the container? No, that wouldn't happen spontaneously. We would have to have some external force here, maybe open this little thing up here and push this over to the side by blowing into it. But spontaneously, that's not going to occur, right? So any added increase in entropy, right, is going to cause some spontaneous reaction to occur. So going back to, if we take a look at this formula here, right? This is solid. These two are now aqueous. Well, which one is more ordered? This one, right? This looks like an increase in entropy, right? Is that now instead of having one substance that's bonded together, it's got nice ionic bonds, everything held nice and tight as a solid, well, now it's more dispersed, right? So this would happen spontaneously, right? Because we have an increase in entropy, right? Because the internal energy is lower here, right? Right? Oop. So looking at this different model here, Right? Looking at this different model is that we have intermolecular forces that are keeping these together. Right? So intermolecular forces that keep these helium molecules together and these argon molecules together. And when we open the valve here, what we consider to be an ideal solution is not going to accompany any additional work. Right? Is that the intermolecular forces between these molecules are identical to the intermolecular forces between these different molecules, right? So these are now allowed to mix. When we open these valves here, is that the intermolecular forces between these two are the same intermolecular forces that we have here, right? And we can consider those to be ideal solutions. Right, so three types of intermolecular forces. We look at solute-solute, solute-solvent, and solvent-solvent intermolecular forces. Now, we can think of this in three different steps, right? When we're looking at a system like this, we're looking at three different steps, right? Is that solute-solute intermolecular forces have to be overcome, right? So in that first step, energy is consumed here, right? It takes energy to separate the intermolecular forces here. It takes energy to separate those intermolecular forces here. But when these mix, right, exothermic reactions release heat. So here, if this energy here is greater than the energies required to split these up, that it's going to happen spontaneously. And that's what this is stating here. Right? Step one is the solute-solute. Those intermolecular forces have to be overcome and we consume energy. The solvent-solvent, they have to those intermolecular forces have to be broken and we consume more energy. And then the attractive force between the other molecules, that's where our energy is released. Right? So we take a look at this diagram here. Right? Here's our solute. And intermolecular forces are keeping those solute molecules together. And here we've broken them. Right? Here's a solvent. We're going to expand that. Those intermolecular forces, we're consuming energy in order to break apart those intermolecular forces. And then here, the attractive force here is larger. The energy here is larger than the energy used to break those apart. And we get this formation here. Right? So, looking at, again, step one, step two, step three, where we can look at exothermic, endothermic, or reactions that aren't even going to happen at all, right? If the change in enthalpy of overcoming those intermolecular forces is less than the change in enthalpy of the intermolecular forces when those molecules come together to make the solution, right, is that's going to be an exothermic reaction, right? Is the output energy is greater than this input energy. And then for endothermic reactions, right, if it takes more energy to break those intermolecular forces than what we get, well, this is considered endothermic. And then reactions that just aren't going to be spontaneous at all. Because even endothermic reactions are spontaneous, right? We could have a spontaneous endothermic reaction. So don't think that spontaneous just consists of exothermic reactions, right? Is that endothermics could possibly be spontaneous. And then we have reactions that just aren't going to happen at all. So this means greater than, and this means a lot greater than. Right, so that's why there's two of these here. So if the energy required to break those intermolecular forces is a lot greater, not just greater, but a lot greater than the output that we get, then the reaction's just not going to happen at all, right? It's not going to be spontaneous by any means. So one of the reactions here, let's see. right? Because even instant cold packs, right? Even these instant cold packs, right? It's an endothermic reaction, but it is spontaneous. As soon as we break this inner bag of water, right? The ammonium nitrate here. I thought I had a video in here. No, apparently I don't. No, I thought I had a video in here when ammonium nitrate goes into water, and you can actually see that it gets really cloudy, gets really clumpy, but it is more disordered than just the water and the ammonium sulfate that we have. Once they're mixed, again, yeah, it gets really clumpy in there. And we can see that entropy is, visually see that entropy is increased. But again, this is an endothermic reaction here. And when we're dissolving, right, when we take some solute and put into a solvent, or some solvent and put into another solvent, some liquid put into another liquid, some solid put into another solid, is that we say like dissolves like, right? This is why I can take one metal, right? I can take silver, solid silver, and I can take solid copper, and we can mix them, right? Because all I have to do is just melt them. They're still in the same physical state, but metal can dissolve another metal. But like dissolves like. So we're going to really just kind of focus on nonpolar and polar substances. Okay. As when we look at nonpolar and polar substances, like dissolves like. Let's see. Is that here, would we consider this to be polar or non-polar? So polar means that we have some polarity. So when we're looking here, is one of these closer to fluorine than the other? Oxygen. So because oxygen is closer to fluorine, it's partially negative, which hydrogen is going to be partially positive. So these two electrons here are being pulled towards the oxygen. And these electrons here are being pulled to the oxygen, and we get some net dipole moment that occurs here. Right? So here, because this bond is polar and this bond is polar, is this a polar molecule? Yeah, right? Here we have the same thing. We have oxygen and hydrogen here again. Is that this is also considered to be a polar molecule. So when I put methanol into water, they dissolve because they are both polar molecules. But if I take some hexane, and we did learn about this, is these polar or non-polar bonds? Rhymes with on-polar. Non-polar, perfect, yeah. So if this is non-polar, this is hexane. When I take this polar molecule and put it into some hexane, is that going to dissolve? No. Because this is non-polar, this is polar, and our general rule is, well, like dissolves like, right? So this is not going to dissolve in water. But if I did this, let's take some let's take some butane. So this is butane. Do we consider this to be polar or non-polar? Non-polar. So would butane dissolve in hexane? Yeah, absolutely, because like dissolves like. Non-polar substances dissolve non-polar substances. Right? Anybody here ride two-stroke motorcycles? Right? What do you have to do to your two-stroke motorcycle when you fill it up with gas? You had to add oil, right? Gas is octane, which is non-polar. Oil is non-polar, and they do mix very well, right? So like dissolves like, right? So there's a reason, there's some, not a reason, but we do use that rules, and we can just say that like dissolves like, and we can see that nonpolar solvents dissolve other nonpolar solutes, and polar solvents dissolve polar or ionic solutes, right? So now let's take a look at some electrolytes here. So electrolytes. So we're going to take a look at electrolytes, define the electrolytes, right? Talk about physical changes that accompany those, dissolving ionic and covalent electrolytes, and then the strength of them, right? So when we look at these reactions here, right, is that just putting these in water. So we have potassium chloride, we're going to put those into water, and then we get some potassium ions plus some chloride ions. And that's different. I already wrote this reaction up on the board for you. So this is sucrose, right? So this is Ch.12 Ch12O11, solid, and then we put it into some water, and we're going to get C12. But this time it's aqueous. So now we'll get a better understanding, because I just mentioned that it was aqueous. We're going to understand the process a little bit more to understand why it's aqueous. But it didn't break up, right? These two broke up here. We get these ions, and this is an aqueous ion, and this is now an aqueous ion. And it's aqueous because these ions are all surrounded by water. Right? So when we take some, what kind of substance is this? What's the difference between these two here? We talked about it just a little while ago. Ionic, right? This is an ionic substance. So when we take ionic substances, we put them into some water, right? Is that atom by atom, each one of these atoms here is going to be separated and surrounded with water, right? Since chloride, right, this chloride ion here is negative, right? It has an attraction to the positive portion of that polar molecule water, right? We discussed this here, right? Oxygen is partially negative, hydrogen is partially positive, and that partially positive end is attracted to that negative end on the chlorine, and just the opposite, right? So here's oxygen, which is partially negative, but it's attracted to that positive port on the cation, the potassium here. So bit by bit, each one of these are surrounded by water now, right? So this is why this is an aqueous ion, right? And the attraction here is that we do have to overcome these intermolecular forces, right? We have to overcome these intermolecular forces. So we have hydrogen bonds here between the water. But here, we see that this attraction here is greater than the ionic traction between each one of those molecules, right? And we can separate them. And this, right, it's like putting a block, like right, sugar cubes here. So let's pretend we just have some sugar cubes. Sugar, sugar, sugar. This is C12H22O11, C12H22O11. So each one of these, right? One of these will get moved out. C12, H22O11, and this gets surrounded by some water. Right? And that's what we're seeing here. Right? Is that in this molecule we do have some hydrogen bonding, right, that occurs here. And we do have water, so water picks off the entire molecule and surrounds an entire molecule of water, right, versus breaking it apart.
And that's why it hydrates you faster than something else.
Well, here, when we're talking about hydrating, is that what happens here is that these here, when we get ions, right, ions will form electrolytes. Right? These are what we consider to be non-electrolytes. Right? So when you're drinking your Gatorade, right, filled with sugar, right? Red Bull filled with sugar, right? Red Bull gives you wings, no, right? It's not hydrating you, right? It might give you a little caffeine boost there, but it's definitely not hydrating you, right? Because there is no electrolytes there, right? But this is the difference between our electrolytes, right, which come from these ionic substances. And again, there are some covalent molecules that will also dissociate this way. But here we consider these non-electrolytes, and these would be electrolytes here. And coming up, so see how these cations, anions are charged here? Right? Is that electrolytes have the capability of conducting electricity because they're charged. Right? You can't conduct electricity through something that's not ionic. There's no charge here. Right? So that's going to be important in just a few minutes here. All right. So water, other polar molecules are attracted to ions, right? And we get this ion-dipole interaction happening here. The ion dipole. So what we mean by that ion-dipole interaction here is here's my ion, and if I put water here, right, we know that there's a dipole occurring here. We just talked about it. We have this net dipole here. This is partially negative here, but this is our anion or our ion dipole interaction occurring between water and this cation over here, right? So we get water molecules surrounded. They solvate. And this process is known as dissociation, right? So this will dissociate, and we'll get some solvated ions here that we consider to be electrolytes. Now, we do have what we consider strong electrolytes and weak electrolytes, right? Just because something dissolves does not mean that it's going to be a strong electrolyte. When substances dissolve in water, okay, if I put this into some water, as long as I don't have too much, which is again what we'll talk about in just a little bit, but all of this will dissociate and create nothing but these ions here. But if I take something like this is acetic acid. If I put acetic acid into some water, well, we do get this. So these are one of our covalent, I know this is a covalent molecule, right? But this is an acid, right? So this acid will dissociate. So it's kind of our exception to the rule here, is when we see acids, okay? So here, C2H3O2 minus. But when this acetic acid gets ionized, right, dissociates here, we're going to get these here. Is it possible for this to conduct electricity? Yeah, it's possible, but what we have to understand is that not 100% of this is going to dissolve, is that only about 3% of this, right? There's still like 97, 98% of acetic acid left, so did it produce many electrolytes? No, didn't produce a lot of electrolytes. So here, produced a lot of electrolytes. So we can consider this to be a strong electrolyte, right? Because all of it dissociated versus some weak electrolyte, right? Could this, as far as conducting electricity, well, which one of these would conduct electricity better? Yeah, the top one, right? Because we have so many more electrolytes in the solution. So we can see that just kind of an example here, right? So ethanol, we take a look at ethanol. We talked about this earlier, right? So ethanol, no conductivity, right? Actually, this is methanol. Let me give ethanol over here. Right? Because when we put ethanol into water, it's not going to dissociate, right? So non-electrolytes, well, it's not going to conduct any electricity. And here we have high conductivity because we created a lot of ions here with the potassium chloride. And then acetic acid, just something that's going to be, it is going to be conductive, right? But the conductivity there is going to be pretty low. So, acids, there's a difference between this weak acid and this strong acid. So we haven't, in 202 you'll cover acids and acid-base equilibria, but let's talk about these two here, is that this is what we consider to be a strong acid. So here this is a weak acid, and this is a strong acid. Weak acids partially ionize, but strong acids will ionize 100%. Right? So this we're going to get. So as far as acids go, right, strong acids anyway, right? So as far as strong acids go, is that this would be highly conductive and this wouldn't be very, still little conductivity here. But even though this is covalent, we talk about ionic molecules, but there are some exceptions when we're looking at acids, okay? Is that those can also be conductive. So now getting to some solubility here, right? Describe the effects of temperature, pressure on solubility. We'll talk about Henry's law and the degrees of solubility. So, highly water-soluble components have a limit to how much you can dissolve. Right. There is a maximum concentration. There's only so much solute you can put into something before it stops dissolving. If I have a beaker of water here and I add 1 teaspoon of sugar and stir it around, is that sugar going to dissolve? Yeah. What if I add 100 scoops of sugar? Not going to dissolve. Yeah, there's a limit as to how much it's going to dissolve, right? So a little story. I'm going on a little tangent here, right? So here's my story on strawberry. Strawberry Quick is my frenemy. It's been my frenemy since I've been little, right? Growing up, you know, nobody was home except my goofy brothers, right? My mom was working, but I get out of work. I got out of school at like 3 o'clock. No, a little before that. I think like 2:50. 2:50, but I only lived a block away from the school. So when the bell rang, I had to run home, because I had to watch Voltron. Voltron was like, that was my show, right? Voltron. Couldn't miss an episode of Voltron. So school lets out, Voltron starts at 3 o'clock, so I had to run home real quick because I couldn't miss Voltron. But before I watch Voltron, I have to make my drink, right? My drink is Strawberry Quick. So I run home and I get a big glass. So we didn't have plastic cups, like we had glass, right? So I got a big glass, put on the counter, then go run to the pantry real quick, and I get the back then, like the Quick used to come in these big metal containers. You have to like pop them open with like a paint can, right? And it pops open that metal top right there. So I get my milk and I pour my milk in, and then I don't even use the small spoon. I gotta use the big tablespoon, right? I get the big tablespoon and I put in there my powder and I start dumping it into the milk, right? And then I start stirring it up, right? And then you hear it grinding right against the glass, right? And then you take a look at it, and I'm not the only one that's done this, right? You take a look and go like, it's not pink enough. Like I need it more pink than this, right? So I start adding mounds of it again, and it's grinding in here. And I know when to stop, because when I look at it, you see that little pink layer at the bottom, right? That little syrupy dark. Oh, now it's done. Now it's done, right? Milk can only dissolve so much Strawberry Quick, right? But I didn't know that. At 8 years old, I had no idea, right? I just needed it in there. And I stopped once I saw that layer at the bottom because there's just a maximum concentration, right? There's only a certain amount of solute that we can put into any solvent before it stops dissolving it, right? So as long as the concentrations, right, when a solute's concentration is equal to that solubility, right, that's when we consider the solution saturated, right? We're kind of at that point of saturation there. When it's less than the solubility, we consider that to be unsaturated. And then we have something we can consider supersaturated, right? So we have saturated when it's equal to that solubility, and when it's less than the solubility, it's unsaturated, right? So I put 1 scoop into my milk, it's unsaturated, but if I put 6 more, we're going to consider it saturated. And then when I see that little layer in the bottom, supersaturated, right? The little pink layer, there is a way to get it to dissolve. And how we can control that is with some heat. That if I were to take that same milk with that layer on the bottom and I put it into a pot and I warm up that pot, I'm adding energy to it, right? Is that those intermolecular forces are now being broken more, right? And that we could dissolve more solution into simply just by heating it up, right? This is the idea. Has anybody here ever eaten or seen rock candy? Right? This is the idea behind rock candy. Right? So behind rock candy, I think I have a drawing of it over here. Right? So here's my drawing of rock candy, right? And we just get some sugar here, we put in enough sugar, and we get it super saturated, right? Super saturated, and then what happens is, once we let it cool down, we get these big crystal chunks that fall out of the solution, right? And that is something that's been super saturated. So we can definitely dissolve it, yes?
Why does it take like crystalline structure? Why does it start forming crystals?
So it starts forming crystals here because there's so much of it. So it's not just going to fall out. Little ones aren't just going to fall out here. Is that the idea behind this is that it's been when we heat it up, the stuff is, we're assuming it's kind of been melted, right? So when we heat up, if we take the idea of sterling silver, right? I take solid silver and I melt it. I take solid copper and I melt it, and I put those together and they mix. When they cool down, right, they're making bonds with each other, but when they cool down, we don't just get copper that falls out of, or rests at the bottom, is that they're intertwined there, right? So the copper just doesn't fall out of the solution like that. And it's just kind of the same idea, is that there's a lot more sugar here. So these sugar molecules here, they form a very strong attraction to this one. And it's going to form a very strong attraction to this one, and a very strong attraction to this one. Is that so when these are heated up and added energy, then collectively, right, is that when they cool down, they all want to just be next to each other, right? So being next to each other like that will create what we call crystallization, and we get these big crystals formed from that. So I hope that helps a little bit. All right. So temperature, right? The temperature in the gaseous state, the pressure is also important here. Right? So we've talked about temperature affecting the solubility, right? And now we can look at pressure also as a form of solubility. Right? Is that all of these are gas, and we see this is the solubility. Solubility increases at what temperature? High or low? This is solubility, and let's take a look at oxygen. So solubility, is solubility high or low right now? High. And is temperature high or low? Low. So at low temperature, the solubility of gas is high. But as it gets warmer, the solubility of oxygen decreases. Which means that in water, there is less oxygen in warmer water than there is in colder water. Right? Any fishermen? No? On warm days, so fishermen during the summertime, right, is that they use lures that will hit the bottom of the lake versus the top of the lake, right? Is that fish breathe in water to extract their oxygen, and if warmer water has less oxygen, colder water at the bottom of the lake has more oxygen. right? This is why fish are at the bottom of the lake during the middle of summer, right? During the middle of winter, well, it really doesn't matter where they're at. There's plenty of oxygen in the lake, whether at the top, whether at the bottom. But during the summertime, well, no, those fish are going to be at the bottom of the lake, simply just because there's more oxygen down there, right? Unfortunately, these fish are gone. They are dead. But this is what happens with, when we get pollution in water, right? Pollution in water affects the temperature, is that at the top of the water, there's just not enough oxygen for fish, right? So we said a dead fish floating, it may, not saying that this is the cause, but it may have been the cause that the water was just too warm where they were at, right? This is simply just water. Right? This happens, right? I've experienced, I just get a cup of water from my fridge, I put it on the counter, and as I come back to it, there's these little bubbles there. Because the solubility of oxygen, as the water's warming up, oxygen becomes less soluble. So now we can see the oxygen coming out of that solution, right? Simply just because it's becoming less soluble, right? When we open our soda cans, soda bottles, right, is that this has to deal with pressure, not with temperature, but with pressure, right? Is that as long as the bottle's sealed, there's a certain amount of pressure there that's keeping the CO2 mixed with this syrup and water. But as soon as we relieve that pressure, well, the CO2 becomes less soluble, and it starts to come out of the solution, right? Divers, right? This is an issue for divers, right? Is that they have to go into decompression chambers, right? Diving at deep depths, that's an increased pressure. So if this diver here, is 500 feet down, 300 feet down, that's a lot of pressure. Is that oxygen is very soluble in their system, in their lungs, in their blood. They have a lot of oxygen there. So if they don't decompress, or if they rise to the surface too fast, that's an issue. Because as they're rising, that oxygen that their body has absorbed in their organs, in their blood, in their veins, in their lungs, becomes less soluble. Right? Starts coming out. So that can really have an effect on them. So they do have to go. But again, that has to do with pressure and solubility. Okay.
Would it also expand?
We can use, yeah. So that's another, that happens with the ideal gas law. Right? So this is Boyle's law. Right? So as pressure increases, volume decreases. So as we're going diving down, pressure's increasing, which means the air capacity, the air in my lung, that volume has decreased now. If I, especially if I have some scuba gear on, right? If I'm down, 200 feet, 100 feet, and I've inhaled in my scuba tank some air, if I start to swim upward, as pressure decreases, volume increases. So that deep breath that I took 100 feet down in my lungs is expanding as I'm rising up, right? So if you're ever diving like that, remember to breathe out on the way up, right? This is why divers breathe out, right? They breathe out that air because it's going to expand. If they don't breathe out that air, their lungs will literally just explode, right? Yeah. Yeah, that's what it's Boyle's law, right? Boyle's law. So we've learned, another thing there. But yeah, absolutely related to that. So pressure has a major effect on solubility, right? So gas solubility. So this is where we're going to consider gas solubility, right? This here, C sub G, is gas solubility. Is there anything else that we can think of when we look at this C here? What else can we?
I know that's.
No, it is. That's we'll say small c, right? So this is a large C, right? But this can also be considered as concentration. So the gas solubility, or think of it as the gas concentration, right? So whenever you see C sub G, this is the gas solubility, but also think of it as the concentration of gas, okay? And then we have this constant here, right? So that constant, that's a proportionality constant, right, for some particular gas liquid system. And then we have the partial pressure of gas. So partial pressure of gas, this is our proportionality constant here. And this is our gas solubility, but also referred to as our gas concentration, gas concentration. So we'll use Henry's law here to determine other information here. All right, so using this formula here, right? So at 20 degrees Celsius, concentration of dissolved oxygen in water exposed to gaseous oxygen at a partial pressure. Partial pressure of gas is 101.3 kilopascals. The concentration of dissolved gas, the concentration is 1.38 times 10 to the minus 3. The gas concentration, the solubility of gas. So this value here is equal to 1.38 times 10 to the minus 3 moles per liter. So it's not going to, and in the problems that you have on the exam, it's not going to explicitly say the gas solubility. It's going to be written similar to this. It's going to say the concentration. And we have to understand that that's our gas solubility when it says the concentration. So here, use Henry's law to determine the solubility of oxygen when its partial pressure is 20.7. The approximate pressure of oxygen in the Earth's atmosphere. So in order to do that, this is what we need to solve for. We need to solve for this proportionality constant. That the solubility of gas over the partial pressure of gas is equal to that solubility constant. Which means that if we take 1.38 times 10 to the minus 3 moles per liter, over the pressure, 101.3 kilopascals, is that this will give us the value of K. So what is K in this case here? That's how we're going to answer this. If I have this partial pressure, but I can determine what this is from some other information, we can determine what that gas solubility is, or that gas concentration is. So what is K here? We have a value? Should be a relatively small value.
We have 1.36 times 10 to the minus 5.
So 1.36 times 10 to the minus 5 moles per liter per kilopascal. So now that we know the value of K, well, let's see what this new solubility of gas is. We know what K is. K is equal to 1.36 times 10 to the minus 5 moles per liter per kilopascal, and we multiply it by our new partial pressure. So at 20.7 kilopascals, What is our new solubility here? We're just going to multiply those together. It's really nice. We don't have to convert any of the units for pressure. We can just simply use the pressure that they've given us.
2.82 times 10 to the negative 4.
Yep. So 2.82 times 10 to the minus 4 moles per liter. Let's do another one. Exposing a 100 ml sample of water at 0 degrees to an atmosphere containing a gaseous solute at 152 torr resulted in the dissolution of 0.45 grams per milliliter. Use Henry's law to determine the solubility of this gaseous solute. All right. So same setup here. We have, let's take a look at this, the 1.45 times 10 to the minus 3 grams per 100 milliliters. This is our solubility of gas. Okay? Just like that other solubility was moles per liter, this is going to be in terms of grams per milliliter. Okay? So this is our solubility of oxygen at 0 degrees Celsius. So this is equal to Cg. So let's put this in. So we have 1.45 times 10 to the minus 3 grams per 100 milliliters over 152 torr. 152 torr. So what is our value of K here?
Times 10 to negative 6 grams per milliliter torr.
Times 10 to the minus what?
6.
Did anybody else get to the minus anything else? What was that?
Yeah, I got negative 3 as well.
Yeah, I'm not getting that. Yes, that's what I'm getting, negative 8. Yes, so I'm getting 9.5 times 10 to the minus 8 grams per milliliter per torr. So grams per milliliter. So now we know what the value of K is. Okay? If you're not getting this value, just come and see me after class. If you're not getting that value. But now we know what K is. We have a new pressure here. So the new solubility for our gas, our new gas concentration is going to be 9.5 times 10 to the negative 8 grams per milliliter per torr times 760 torr. So this unit cancels this unit, and we something in grams per milliliter. So what is our final answer there? What is it? I'm sorry?
7.22 times 10 to the minus 5.
So 7.2 times 10 to the minus 5 grams per milliliter. All right. A couple more here. Certain species of freshwater trout requires a dissolved oxygen concentration of 7.5 milligrams per liter. So that's what it requires. Could these fish thrive in a thermally polluted mountain stream at 30 degrees Celsius? Partial pressure is 0.17 atmosphere. And then we have to look for some, so we need to estimate something here. We're going to estimate what K is. So K is still equal, oh, we can still use this up here. So this is what K is equal to. So I believe this is what they're wanting us to use here. All right. This is, it's not, oh, there it is right there. Okay, good. So this is done at 1 atmosphere. So this table here comes from 1 atmosphere. And the solubility of the gas of oxygen at, what does it say, 30 degrees? So here's 30 degrees here. So I think 1.2 is a pretty good estimate. Let's go with that. So we would say 1.2. So this is going to be 1.2 times 10 to the minus 3 moles per liter. Divided by 1 atmosphere is going to be 1.2 times 10 to the minus 3 moles per liter atmosphere. So this is our value of K. So now that we know that value here, we have our partial pressure. So what is the solubility at 0.17? Because this was at 1 atmosphere, right? So the solubility is going to be 1.2 times 10 to the minus 3 moles per liter atmosphere times 0.17 atmospheres. So 1.2 times 10 to the minus 3 moles per liter.
2.04 times 10 to the negative 4.
And we're talking about oxygen here, but I don't think we've answered that. We know what the solubility is, but it's asking us here that the dissolved oxygen concentration is milligrams per liter. So we're going to have to do some stoichiometry, some dimensional analysis here, not so much stoichiometry. So we'll do some dimensional analysis, and we're going to convert 2.04 times 10 to the minus 4 moles per liter. We know that we're using oxygen. So oxygen is 32.0 grams of O2 for every mole. Oh, I have this backwards. For every mole of O2, we have 32.00 grams of O2. And this wants it in terms of milligrams per liter. So then we have, this is grams. So we're going to have 1 gram in every 1,000 milligrams. So this unit cancels this unit cancels this unit, and milligrams per liter. So what is that value there? 2.04. Comes out to a nice number. What is it?
6.528.
So 6.528 milligrams per liter. So at 30 degrees Celsius, the oxygen 6.5. If trout need 7.5, would they survive in that polluted lake, the river? No, it's below this threshold here. right? They need that stream of water at 30 degrees, right? It's not survivable for those trout there, right? They're just not going to survive. But now let's take a look at this at 15 degrees Celsius. So at 15 degrees Celsius, what is that value there? So first we're going to do this, right? We're going to do we'll go back up here. This is done at 1 atmosphere. And at 15 degrees Celsius, our solubility of oxygen is now about 1.5. So 1.5 times 10 to the minus 3. So we're going to have 1.5 times 10 to the minus 3 moles per liter per atmosphere. So this is K. So at 15 degrees Celsius, the solubility of gas, oxygen, is going to be 1.5 times 10 to the minus 3 moles per liter atmosphere times 0.17 atmospheres. So what is our new solubility here?
We got 2.5 times 10 to the
2.5
5
5
times 10 to the negative 4.
times 10 to the negative 4. So now we'll take that. So we have 2.55 times 10 to the minus 4. This is going to be in moles per liter. And we'll do the same calculation here. We'll put 32.00 grams of O2 for every mole of O2. Multiply that by 1,000 milligrams. 1 gram, cancel, 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 cancel. And what is our new solubility here?
8.16.
Right? So here, so at 15 degrees Celsius, and this is at 30 degrees Celsius. So no fish in the summertime, but maybe in the wintertime, these fish are going to return because now they can survive. All right? And yep, just a few more minutes to finish this off. So solutions of liquids and liquids, right? So liquids can be dissolved in other liquids. And they're both solute and solvent can both be liquids. So when we dissolve a liquid into a liquid, right, there's terms for that, okay? If they mix really well, then they're considered to be miscible, right? I don't know who drinks this delicious drink here during the middle of summer. I hear it's fantastic. I've never drank it though, right? They're called micheladas, I hear, and I hear they taste wonderful. But, right, you take some beer, you take some Clamato, mix them around, you get this nice little solution here, right? But these are miscible, right? Miscible solutions, right? Salt water, miscible solution. For those that you work on your car, right? You put antifreeze. You make a 50-50 mixture of antifreeze and water, right? 50% antifreeze, 50% water, but those dissolve in each other. Those are miscible solutions. I'm not telling anybody to make this drink, right? But if they mix well, right, then we can call them miscible, okay? Take chocolate syrup, put it in milk, they make chocolate milk, they're very miscible, right? Those are miscible together. And when they don't, right, those are really considered immiscible, right? Oil and gasoline. We mix oil and gasoline together, those are miscible, but if we put non-polar liquids and water together, right? Oil and water don't mix, right? These are considered to be immiscible, right? So we have miscible and immiscible. So when the two liquid mixtures, right, don't mix, there's a layer of oil, here's our layer of water, is that these are considered to be immiscible. So miscible and immiscible, and I believe that finishes us off for this portion here. All right, so we covered parts 1, 2, 3, so parts 4 and 5 on Thursday. We have our lab tomorrow.